Hello, this is János, it is Real World Audio, and today we will look into something really special, and that is hum. Amplifiers hum, and specifically single-ended tube amplifiers hum level. And why is that important? That's important because if you want to know how loud your amplifier will be humming, how good the power supply you need to design to be quiet, then basically you have to look at the ripple at your high voltage to get a ballpark on how loud your amplifier will be humming. So this is a main component for the amplifier hum, and when we design the power supply, this is of key consideration to get that ripple, which means hum, down to an acceptable level. And I'm going to go through a little explanation how you can calculate the hum level, the ripple level for a specific power supply, and then I will give you a tool how to translate this hum level that you have received from your simulation software, or if you want to, you have an actual amplifier. If you measure the hum level, the ripple of the B+, then based on that you can calculate what is the output on your loudspeaker or even at your listening position, how much that will contribute to the hum that you hear. And of course, now before we go into more detail, I have to add that this is not the only component for hum in your amplifier, but this is pretty much the main component for hum that your amplifier makes, and pretty much the only one that you can do a nice hard calculation for, because the other source of hum that's coming from your filament supplies, which is not an issue if you have an indirect heated triode where the filaments are properly referenced, and but it's a very big issue for direct heated triodes where the filament hum appears on the signal. And I'm going to touch base on this very a little, just a tiny bit, but not going to it too deep because that would take too much time. So now we will just focus on this B+ hum by itself. So what you see here, that's Power Supply Designer program, and I'm showing a very typical triode power supply here, where you have a power transformer, then you have a rectifier tube, in this case a 5AR4, which is pretty much the most common rectifier tube ever, and then a single pi filter power supply with an inductor and a capacitor, plus it's a capacitor input supply that you can tell by that largish value capacitor in the front. So this is the C1 capacitor, and that's C2 capacitor, and that's the L1 choke. And here in the circuit I put in a resistance of a 3.5 kilo ohm to simulate the load that the tubes present for the power supply, so that this software can work with it and simulate what is the ripple, what is the hum at that specific load, that the current load that the vacuum tubes give this power supply. So this is something that's a little bit reminiscent of what you would see for a type 45 or a 2A3 amplifier, something like this. So most of them that you can buy commercially, this is like a typical commercial low power single-ended triode power supply. That there is like a nice choke in there that does most of the filtering, and as you see, what are we getting here? I chose these values because this is something very close. I'm going on top of my head, but the Yamamoto tube amps, if you are familiar with them, they use something like this. They have 47 microfarad for the C1 position, they have 40 microfarad for the C2, and have something like either a 6 Henry or a 7 Henry choke in there. So basically this is kind of like the Yamamoto power supply, if you were wondering about it. And then when we run the simulation, then we can read, it shows all kinds of things. I'm going to make, I think I will make a video series on how to use Power Supply Designer. So right now I'm just going to fixate on this part. So if you click on the VR1, it shows the voltage on the R1 resistor. Basically that's the output, the voltage output of this supply. So as you see here, minimum value, maximum value, and there difference is shown there between minimum and maximum. So we see 163.9 millivolt hum. So basically that is what's going to be affecting your loudspeaker. However, it's not going to be 163 millivolt hum out, because there's an output transformer, and the turns ratio will cut this hum that much lower. So now let's go into this hum calculator. This is an Excel calculator that I made, and now I'm just following the train of thought, what is happening. So we have received what was the B plus hum. So let's put it in here. So the values which are green, we can enter values here. So it was like essentially 164 millivolts. Primary impedance, we write here what is the primary impedance of the output transformer, and let's say we put 5 kilo ohm here. And what is the secondary impedance? 8 ohm. We have the loudspeaker connected to the 8 ohm tap, okay. And then it calculates for us with red the turns ratio. So basically it is the secondary winding is 25 times less turns compared to the primary, and that also means that the output hum, the hum voltage that you can measure with your oscilloscope at the output will be 6.6 millivolts. Now that's darn loud, right? If you know, then you know that what we want is 1 millivolt or less hum at the output of the amplifier. That makes a reasonably quiet amplifier. 6 millivolt hum will make a pretty loud hum. So going for speaker impedance, depending on what is the speaker impedance, it will change the hum level. So now let's just assume we have an 8 ohm impedance loudspeaker, and then we'll get the calculation hum power. What is the power that is generated on your loudspeaker by this ripple? And the dB level, so below 1 watt level, minus 53 dB. And now here with the green one, we can input what is the sensitivity or of the loudspeaker that we are using. And let's say we are using a 92 dB per watt meter loudspeaker. And then it will calculate for us here what is the audible hum at 1 meter distance. That's 39 dB. That's pretty noticeable. That's like a quiet talking level, that loud hum. Now, how far do you sit from the loudspeaker? Let's say 2 meters, and then it's 33 dB at your listening position, provided you are listening to one loudspeaker. So this will give you the channel for, the hum level for one channel, not the two loudspeakers. So this is hum per channel. And then you add together that for two loudspeakers. It depends how well the two loudspeakers couple, so and your room as well, how big your room is. So that's why it's not really possible to just give a fixed calculation for the two speakers, because the actual hum will also depend on your room reinforcement, how big your room is. The smaller it is, the louder it will be, and also depending on the positioning of the speakers, how good do they couple with each other, or they cancel out the phase at the listening position at the frequency of the hum. That might impact it. So basically, in real life, what you can expect for a stereo loudspeaker is something like between +3 to +6 dB compared to this level. So something similar to what the hum is calculated for 1 meter. But this is darn loud. And if you have a Yamamoto, then you know that it doesn't get this loud. It's much softer. And how much softer it is, because you see that the B plus hum is 164 millivolts. And now when you notice that there is a filament pot with single-ended triodes, direct heated single-ended triodes, where you can fine-tune the filament's hum level. It's called the hum pot. And if you position it to a certain position where it cancels out the ripple, so the filament is in opposite phase compared to the ripple, then it can cut it down significantly. And how significantly? Maybe it can cut it down like 4 times. So if we have like cut it down to 40 millivolts, then or a little bit better than that, maybe let's say like 25 millivolts or so, that's a good ballpark, like a 5 times cut, 6 times cut, something like that. And then we are getting 1 millivolt hum on the output. And now what does that translate to with a 92 dB efficient loudspeaker or sensitive loudspeaker? At 1 meter, it's 23 dB hum. And now that's soft enough, so if you have a busy day or leave it at a busy place during daytime, that hum will be noticeable, but it will be very soft, so it doesn't bother you. However, if it's late night and you live in a very quiet place, then 23 dB will be kind of like on the little bit bothersome region. So why is this calculator important? For one thing, now we have just looked at it using Yamamoto as an example to see how it works, and why do you need that hum pot on the filaments, because if you don't have it and it's set at the worst position ever, where the filament doesn't cancel out, then you can expect hum at this level. And yes, when you look at it and when the hum pot is not set correctly, you have pretty loud hum, and then you can quiet it down really significantly. And so that's like playing around. You can play around much more with this calculator, but now I am 14 minutes, so we will continue from here, because toying around, inputting values here, you can learn so much about hum level, so much about how it relates to loudspeaker sensitivity or efficiency. And yes, so the Power Supply Designer, this software here, that's freely downloadable, and you can try around, like if I change the the choke, the inductor, to a different Henry one, a different impedance, different DCR one, or I change the capacitance here, how will it affect the power supply, and then you will get a certain millivolt of hum at the end on the B+, and then you can plug it in here to this calculator, and this will give you, when you plug in all the data from your amp, which is the primary impedance of the output transformer, the tap you are using, the actual impedance of your loudspeaker, and the sensitivity of your loudspeaker, how far you are, and that will give you the hum per channel. And how can you get this calculator? So if you go to my Buy Me a Coffee site, how bad thing from me to say something like this, buy me a coffee, geez, this guy is asking for money, what a shame. So anyway, so when you go to the Buy Me a Coffee site, then it says featured extra, and it says high voltage ripple to loudspeaker hum level XL calculator. So when you there's a link there, and you click, it should take you, wait, it took me to my channel, yay, no. So I think you then have to click there. When you click on that $6 sign, yes, I'm so shameless, I'm asking $6 for this. Geez, that's a king's ransom, and surprise, surprise, you can't even get a coffee for $6 at Starbucks. Not here in Honolulu. So anyway, when you click on get this, I think it doesn't let me get this because this is my Buy Me a Coffee page, but so it looks like I cannot buy it for myself, from myself. But when you are here, you can click on that. There's a little bit of an explanation what it does. So there you go. If you want to play around with it, you can play around with it. And if not, I just told you what this calculator does. You can build your own calculator if you want to. It will take you a couple of hours, and probably a little, that includes research. It also includes knowledge of Excel, and if you don't know how to research it out, or you don't know how to program Excel, then maybe that $6 is much less than the effort you need to put in to go through all that hassle to build that calculator for yourself. And we are going to calculate from here at the second part of the video, where I will show why is this calculator important, because I have created this calculator because I find it useful. When I'm designing an amplifier's power supply, I use it a lot, and it tremendously speeds up the design process, talking from experience. That's why I decided to share it, and I thought that, you know, there's this Buy Me a Coffee thing, and you can donate me this coffee thingy. Then if you want to donate, then why not get something in return instead of just giving me money for nothing. So thank you guys for tuning in, and those of you who have already got this, wink wink at Corey, thank you for doing that, and I really hope it will be helpful for you, and I know that it will be. So thank you, have an awesome, wonderful day, bye bye.